I guess we're going to be transitioning from the last bunch of talks about talking about the actual geology of the moon to talking about a process to go and how we're going to figure it out in the future. And so this is not actually going to be talking about the moon. It's talking about a mission to the Mojave Desert as an analog for going to the moon in the future. And with that, our mission will be the Mojave Volatiles Prospector, and we'll be looking for water in the desert. And so we're going to talk about just how that process is going to happen and the relevance for a lunar mission in the future. So the looking for water on the moon is like one of those great stories, I think, of recent lunar science. When I was first learning about the moon, I heard about the story from the Apollo samples looking for water, finding their bone dry is kind of what we learned, or at least what I learned growing up as a student. And in the years since then, just discovery after discovery, mission after mission have kind of chipped away at that and pointing to a whole new paradigm for what water and volatiles story on the lunar surface is. From reanalyzing the lunar samples, getting hundreds of parts per million of water in the subsurface, to spectroscopic observations, seeing water and hydroxyl observations near the poles, to the L-Cross mission finding substantial water deposits in the near surface regolith. And all this has kind of really changed what we think is possible on the moon and has really important consequences for the exploration that we want to have in the future years. Especially this kind of polar water that's trapped in the permanently shallow craters that has the kind of volumes that could be important for exploration purposes. This here is a map from Diviner Data looking at kind of the south pole and the water associated with these permanently shallow craters. This is a depth to water map showing that all around these kind of permanently shallow craters we see these distributions. Now this is an incredibly great map for showing what is a large-scale distribution and how they're kind of associated with the permanently shallow craters. But if we ever actually want to make use of this water, the volatiles, we really want to know a lot better what is the distribution. Is it continuous from these shallow craters, or is it blocky, splotchy, discontinuous? Is it located as close to the surface as we observe? What is the distribution at depth? All those kind of questions are key to kind of using this more. And so tomorrow morning, I believe one of our co-authors will be talking about the resource prospector mission that is proposed to send to the pole to kind of examine and exactly map out what is the volatile distribution here. And so if you want to know more about this mission, come tomorrow morning at 8:30. Right now we're going to talk about how we're getting ready and answering a lot of the questions that this rover will have. And so this mission will send a Veneer spectrometer, a neutron spectrometer, and a drill, some of the main instruments of the package, to kind of map the surface, figure out just what is the nature of these volatiles, how is it distributed, and where in the soil column is it located. And this process has left a lot of open questions that we'd like to answer before actually committing the resources to go into the moon. How do we actually map hydration distribution? Someplace that's going to be variable with area, but we only have a single rover traverse to actually map it. How do we go from a line to an aerial map? Is a big question that we're kind of handling or working to deal with. How do we actually combine the data? The neutron spectrometer, visible, near-infrared spectrometer look at very different things, very different surface penetration depth. How do we kind of bring those data sets together to really map a surface? Do we give more credence to one data set versus the other? How do we actually get those to work together? And how do we kind of get rid of all the interface issues between instrument data, people data, consideration, and really maximize our driving so that way we can cover as much area as possible? All those are things that we'd like to test in the Mojave coming up this fall. Luckily, the mission that we have this fall has a bit of heritage. So in 2012, this mission went to Hawaii, had many of the same instruments, many of the same processes, and kind of tested a lot of these questions just to make sure all the systems work together. They had a rover with all the instruments, this whole backroom site where the real-time data observations happened, working with a science-backed team to kind of figure out what does that data actually mean, and how do we turn the observations into kind of a traversable plan. And then roving around the Hawaiian volcanic analog allow a kind of test bed in a similar lunar environment. For this mission, with a big difference between what they've done before and what we want to do now, is that here the kind of targets were known. So they drove around and found these hotspots, basically targets with known hydration that they're able to say, okay, we are now in a hydrated hotspot, we know what that is, and we found it. And so this had clear targets in 2012. And that's the one thing that we really want to push beyond in the Mojave Desert, where we are just going to look at the natural hydration of the surface. And we won't really know, like, we have to figure out exactly what does it mean to be, yes, this is hydrated, this is a hot spot, or target of interest, or whatever we want to call it, that, this is where the water is. So we won't have a clear-cut definition. So to define what that looks like, this is kind of an observation of what the data running in real time looks like. The neutron spectrometer here is showing with counts of neutrons. When it kind of hits one of these targets, it gets a spike there, and that in that data shows that we're on a target from the 2012 campaign. The near surface infrared value is a bit more complicated. This band here is showing our a band parameter of the 1.5 water band, and here we see that it's occasionally associated with this known hydration. Other targets are not quite as clear. So what does it actually look like when we look at mineralogical samples in a known planetary analog, and how do we get these two instruments to work together to really combine and create the maximum amount of information? So the main goals of the Mojave mission is, first of all, again, that main thing where we want to get the spectrometer, neutron spectrometer working together, understanding just how the data sets coalesce together in a way to not only understand volatiles, but understand the geology of wherever we are. We want to get better at taking that data from the instruments and working through the science team to understand just where we are on the surface and how do we turn those observations into actually a traversable plan. And then, just because this is a lunar analog inspired mission doesn't mean we can't actually do science of where we are. So understanding the Mojave Desert, just to understand what an arid environment is, a very worthwhile goal on its own, and is one of the main focuses of this, is just understand what the Mojave is given the instruments we have. So given that, what is the target area we're looking at? The Mojave Desert is going to be our goal. It's a very arid part of, well, the Mojave Desert makes up most of, a large part of Southern California, part of the Basin and Range province, very, very dry. We're going to be going in October, just as the summer temperatures kind of ease off a bit, and right after a bit of a late summer, this is, again, you see precipitation here, that's 0.4 inches. So it's not much, but hopefully there's enough water in the area that we can actually observe, is the hopes of going in October as well. So we're going to be visiting an alluvial flan, elevation about 450 meters, going here just off I-15. Now on the moon, we can basically come in from the sky, land any place that's engineering safely. Where on Earth, we have to actually truck in our rover. So having access to roads is a serious constraint when we have lots of people and equipment and all that kind of bring it in. So looking at the field site areas, that was one of the main criteria of kind of figuring out where we want to go. We lose in colors. Good? Okay. So within this area, we chose this alluvial fan for a whole bunch of reasons. Within the area, we could actually go from a technical standpoint. This is one of the places that had the most diversity. Both of these washes, you can see the light tone streaks there, had a diverse of mineral textures. Both small grain, dust, dirt, as well as the more rocky, dark tone areas. So we have a diversity of areas, a diversity of topography in that as well as kind of sourcing a whole bunch of different rock types from the mountains that then spread out. So we have as much diversity as we're allowed in this site. So that's kind of how we decided to go and explore this alluvial fan. Now, Mojave Desert has been studied a lot. So was a study of breaking all the different desert pavements into different zones, and initial studies that kind of made this into what we realize is a good lunar analog. Early resistivity studies have shown a water content of 2 to 6 weight percent water, compared to what L-Cross has seen in the polar environments of the moon, about 5 to 6. So we're hoping it's more on the 5 to 6 side where we are, but it's hard to really tell before we go out there. But again, this kind of rocky pavement, deflation surfaces is going to be our main target goal for this mission. Now this is where we kind of figure out what we know about the sites. There's going to be 2 parts of the team, an in-sim and out-of-sim team. I'm currently in-sim, which means I don't know anything more about this site than I would know about a site of the moon. I can look at it with worldview data. It has meter to sub-meter pixel resolution. That's kind of the best mapping I can get of it. We can also add hyperspectral data, the Hyperion data has 30 meters per pixel, which before we actually look at it at all, we degrade down to 140 meters per pixel to get kind of an M cubed kind of site there. And so that's how we can kind of get an idea of what's going on for the people who are actually going to be doing the science, who want to keep in the kind of a lunar perspective. The advantages here, we can see this is just a false color image showing some of the spectral variability. We do see that there are different spectral zones along the fan, which hopefully will result in different spectral qualities that we'll see of our instruments and can maybe map out just what the differences are and how that might relate to hydration. Now here's zoomed in, kind of seeing the individual washes, and this is our best view of what we think the rover will be driving on. We can examine the washes, which may contain more hydration, places where water flows, may have hydration either in mineralogy, ultramineralogy, or may stay close to the surface compared to the more rocky areas that may have water carried in a different way. You know, maybe it's within the rock mineralogy itself or buried just protected underneath that. You see these big spots here are the bushes, which are not really a great lunar analog, although from a trafficability, it could be a large lunar ejector rock that we have to be able to drive around. So that's a good thing to just practice on the trafficability aspect. And so just a little look in what we're going to be doing. Basically segmenting the fan into areas, which will then create traverses. We have some nominal places we want to go based on the spectral data that we do have. And then using kind of real-time data, looking at the data every single day as it comes down, real-time essentially, and then planning, okay, this is a place we have elevated signals of neutrons. Let's begin different mapping processes, raster mapping to kind of try and get some aerial aspect into our single one-dimension traverses and build up a map in that sense. And all the time was we're going to be talking with these, kind of integrating the knowledge of the science team within that process. And I think that's my time, so I'll take any questions you may have. So hopefully in the next year's Lunar Forum, we will actually have some more answers and data to actually share. That's the goal. Yes?
Question. With, of course, the instruments on the moon, we're looking at frozen water, and here you're probably looking at liquid or, I don't know, rinds of vapor or something. I don't know. Is there any difference in the instrument response to those different kinds of water, and do you take that into consideration?
I don't think we're actually I doubt we'll actually see liquid water. I think more of a minerally bound water is probably the most common thing we'll see, but a liquid sense. And I think that's doesn't really matter so much for the neutron spectrometer. That just has neutron sources and should see them across the board for any types of water's forms. Ices do have a different spectral character. So if there was ice on the surface, that would look very different spectrally than buried water, which we wouldn't see at all with, or buried water of any form that we wouldn't see at all. So that would be a big difference if we're actually going over ices. And so if we are seeing ices, that would be even better suited for the particular instruments that are part of this package.
So kind of as a follow-up to her question, do you have future plans to test the rover in regions that actually would have ice on them?
That's a great idea, and we'd love the funding to go do that. So that would be, I think it's a funding limited issue. So I think that would be an amazing next step in the progression of this. So we're focused on this mission now, but that's definitely something that's worth consideration.
Okay, thanks.
Hey, JR, it's Rick. For Barb's question, there is a difference between going to the moon and looking for stuff and going out to the Mojave. In terms of the neutron spectrometer, you need to take your neutron source with you to the Mojave, which introduces some interesting complications. But going to the moon, you don't need a neutron source because you've got one ready-made by galactic cosmic rays interacting with the surface. And so the moon's surface you can think of as a glow with neutrons, whereas what we need to do out in the Mojave is take our neutron source with us. So that's one major difference. And the response of the instrument is different in those two cases.
Okay, rounding out our